Recently, very important news has emerged about Artemis mission, SpaceX, and a lot of news. The first news with us says, Japanese astronauts will join NASA moon landings in return for lunar rover. The first non-American to walk on the moon will be a Japanese astronaut. Based on a new agreement between the United States and Japan, President Joe Biden announced the goal during a state visit by Japan's Prime Minister, Kishida Fumio. The science and education ties between Japan and the United States stretch up to the moon, where 2 Japanese astronauts will join future American missions. And one will become the first non-American ever to land on the moon. To date, only 12 humans, all Americans, have landed on the moon as part of NASA's Apollo program. From 1969 to 1972. The USA Artemis program seeks to return astronauts to the moon as soon as late 2025. With the first landing targeted for the program's 3rd mission in 2026. The 4-member Artemis II crew includes the first woman, the first person of color, and first non-American to fly to the moon, the latter a Canadian. The new Lunar Surface Exploration Implementing Arrangement, signed by NASA Administrator Bill Nelson and Japan's Minister of Education, Culture, Sports, Science, and Technology Masahito Moriyama, does not specify on what Artemis lunar landings missions the Japan Aerospace Exploration Agency astronauts will fly, but does note that the flights rely on important benchmarks being met. Japan will develop for NASA's use a pressurized rover. It is going to lead us to cover ground we've never covered before, because we'll be out and can stay for several days on the surface. That means cover it literally, scientifically, and diplomatically. Since 2019, JAXA and Toyota have been collaborating on the development of a pressurized lunar rover that incorporates Toyota's fuel cell technology to provide power to the vehicle. The lunar cruiser, which was named after Toyota's Land Cruiser, is designed to serve as a camper van for multi-day excursions. It is a mobile habitat, it's a lunar lab, a lunar home, and a lunar explorer. It's a place where astronauts can live, work, and navigate the lunar surface. Japan will not only provide the new pressurized rover, but also operate it on the lunar surface, with or without astronauts on board. The lunar cruiser, which NASA will launch and deliver to the moon, is expected to ready by 2031 for use by the Artemis II crew and then serve subsequent missions over the course of 10 years. The pressurized rover will be a powerful contribution to the overall Artemis architecture as Japan and the USA go hand in hand with international and industry partners to the lunar surface and beyond. JAXA is ready to assist MEXT and push this forward with our science and technological expertise to establish sustainable human presence on the moon. The Japanese rover is intended to complement a smaller, unpressurized vehicle now being developed by 3 USA companies. Intuitive Machines, Lunar Outpost, and Venturi Astrolab are each working on concepts for a lunar terrain vehicle for use by Artemis astronauts on shorter range excursions, in addition to landing 2 Japanese astronauts on the moon. NASA and JAXA have previously agreed to fly a JAXA crew member to the Lunar Orbit Gateway in return for Japan providing the human-tended platform's environmental control and life support systems, as well as augmenting its cargo transportation needs. What better representation of the promise of partnership than President Biden's announcement today that America will no longer walk on the moon alone?
The second news with us says, SpaceX launched its second national security mission of the year Thursday, April 11th. A Falcon 9 rocket lifted off from California's Vandenberg Space Force Base at 10:25 a.m. EDT, on a mission for the USA Space Force called USSF-62. USSF-62 will send the Weather System Follow-on Microwave satellite to low Earth orbit. WSFM is a next-generation spacecraft that will provide critical and actionable weather intelligence to military operations in all warfighting domains. WSFM's primary instrument is a microwave imager, which will measure sea surface winds, the strength of tropical cyclones, and gather other environmental data. Also flying on the satellite is a space weather sensor.
The next news with us says, NASA's Lunar Reconnaissance Orbiter snapped a perfectly timed photo as it crossed paths with another spacecraft orbiting the moon. The LRO, which has been orbiting the moon for 15 years, captured several images of the Korea Aerospace Research Institute's Danuri lunar orbiter as the two spacecraft. At the time the photos were taken, Danuri was orbiting below the LRO, which was flying 50 miles above the moon's surface. Relative velocities between the two spacecraft were about 7,200 miles per hour. NASA officials said, making it challenging for the LRO's narrow-angle camera to hone in on Danuri. The LRO's camera exposure time. NASA's LRO had 3 opportunities to snap photos of Danuri during close flybys. For the first snapshot, LRO was 3 miles above Danuri and oriented down 43 degrees from its typical position looking down at the lunar surface. In capturing the orbiter with its new positioning, Danuri appeared sort like a disc-shaped streak across the
next news with us says, space weather can make it hard to predict satellite trajectories. Here's why that's a problem. Satellites in low Earth orbit can venture hundreds of miles off their expected trajectories when bad space weather hits. The problem affects the International Space Station, China's Tiangong space station, and many Earth-observing satellites that need a close view of our planet. Experts say this positioning uncertainty increases the risk of dangerous orbital collisions, which threaten to worsen the space debris problem and make the space around Earth unsafe. At altitudes of 500 kilometers, 310 miles, we can determine the position of our satellites with the accuracy of 2 centimeters. CEO of California-based satellite company GeoOptics, which makes meteorological measurements of Earth's upper atmosphere. But at lower altitudes, it becomes a big problem. The lower the orbit, the bigger the inaccuracy. That's because space weather affects the density of Earth's upper atmosphere. As atmospheric density naturally decreases with altitude, the variations caused by space weather are bigger closer to Earth. The higher the density, the more drag satellites face, which slows them down and makes them sink toward Earth. At the lowest altitudes, satellites can be hundreds of miles off their predicted paths when too much solar wind blows from the sun. Altitudes of around 400 kilometers and lower are the worst hit. It's exactly in these orbital regions that some of the most valuable spacecraft fly. The International Space Station circles 250 miles above Earth, and Tiangong resides only slightly higher, at 425 kilometers. Researchers are increasingly eyeing these very low Earth orbits because they provide a detailed view of Earth, and plans are underway for new missions to operate in this space. The lower you get into the atmosphere, the better you can do on certain kinds of measurements. For example, radar measurements get much better the lower you can get. When satellites run out of the fuel that helps them maintain their altitude, they begin to spiral downward. On their way, they pass through this region of higher uncertainty, posing a threat to operational spacecraft. Trajectories of satellites and pieces of space debris are determined many days in advance, using measurements by ground-based radars and optical sensors. But a strong burst of solar wind from the sun can throw these predictions completely off. This creates challenges for spacecraft operators as they struggle to ascertain how close their spacecraft might get to other objects. It's an ultimate thing to answer, because the operator must decide whether they are going to perform a collision avoidance maneuver or not. If they decide to maneuver and space weather changes, that changes the drag profiles and where and how close things come together. It may negate the maneuver and actually increase the risk. Satellite operators plan collision avoidance maneuvers several days and many orbits in advance. But space weather forecasters have a very limited understanding of what the sun will do next. Coronal mass ejections, massive bursts of superheated plasma from the sun's upper atmosphere, explode from sunspots without warning and take 2 or 3 days to arrive at Earth. Moreover, scientists can generally only measure a CME's strength about 30 minutes before it hits the planet. When it passes the Solar and Heliospheric Observatory, a spacecraft jointly operated by the European Space Agency and NASA, some 1.5 million kilometers from Earth. If you have a warning that's out an hour in advance, that's probably not sufficient to get the command and control to get the maneuver planned. And it's not just the sun's day-to-day behavior that is not well understood. The number of sunspots, solar flares, and CMEs that arise from the star varies on longer timescales following a roughly 11-year cycle that swings from a minimum through a maximum to the next minimum. The problem is that each solar cycle has a different strength, and therefore spacecraft operators can't plan ahead, as they can't predict how bad space weather will be during their next mission. A more active cycle means spacecraft will face more drag, and as a result run out of fuel faster and deorbit sooner. The differences might be substantial. The last news with us says, what happened when the moon turned itself inside out billions of years ago? Over 4.2 billion years ago, the moon turned itself inside out to create the lunar surface that has become familiar to humanity. Most scientists would agree the moon was created around 4.5 billion years ago, when another massive body in the solar system smashed into Earth, flinging molten material into space that coalesced as our natural satellite. How the birth of the moon proceeded after this violent start, however, has been described as more of a choose-your-own-adventure novel. They say there are many possible paths Earth's natural satellite could have taken to form in full, ultimately leading to the Moon-Earth system we see today. The team of course has its own ideas about the major incidences that might have formed the moon. The researchers say rock samples collected during the Apollo mission, for instance, may indicate there was a time when the moon flipped inside out. This result, if true, might also solve a lingering mystery about the moon's composition. Titanium on the near side of the moon. Basaltic lava rocks brought back from the moon have shown surprisingly high concentrations of titanium. In addition to this, satellite observations have revealed that titanium-rich volcanic rocks are primarily located at the lunar nearside. This left scientists scratching their heads about how these particular rocks got there and aren't more widely dispersed. The University of Arizona team suggests the moon formed rapidly, leaving it entirely covered with a hot magma ocean at first. As this ocean cooled and hardened, it would have formed the outer layers of the moon, including its mantle and crust. Yet, at lower layers, the infant moon would have still been in turmoil. Models of moon formation suggest the last remains of this giant lunar ocean crystallized into dense materials including ilmenite, a mineral rich in iron and titanium. Because these heavy minerals are denser than the mantle underneath, they created gravitational instability, and you would expect this layer to sink deeper into the moon's interior. Questions remain: would this material sink all at once as a single blob after the moon solidified? Or a little at a time as smaller blobs? And, if it sank within the interior of the moon on a global scale, how did some of it rise to carry titanium to the moon's near side? Without evidence, you can pick your favorite model. Each model holds profound implications for the geologic evolution of our moon. Co-author and Peking University developed models that suggested a giant impact on the moon could have caused a dense layer of titanium-rich material beneath the crust to shift to its near side. Once there, this material would have sunk, formed sheet-like slabs, and cascaded to the interior of the moon, leaving a remnant beneath the crust in the form of intersecting bodies of dense titanium-rich deposits. The Grail of moon formation models. To solidify its molten theories of titanium-rich ilmenite material and observations of the moon, the team turned to data surrounding lunar gravity anomalies detected by NASA's Gravity Recovery and Interior Laboratory Dual Spacecraft mission. Analyzing these variations in the moon's gravity field allowed us to peek under the moon's surface and see what lies beneath. This confirmed that Grail data conforms with ilmenite layer simulations. Such confirmation also showed that gravity field observations could be used to trace the distribution of ilmenite remnants left behind after a majority of the dense layer had sunk to the deep interior of the moon. Our analyses show that the models and data tell one remarkably consistent story. Ilmenite materials migrated to the near side and sunk into the interior in sheet-like cascades, leaving behind a vestige that causes anomalies in the moon's gravity field, as seen by Grail. To solidify its molten theories of titanium-rich ilmenite material and observations of the moon, the team turned to data surrounding lunar gravity anomalies detected by NASA's Gravity Recovery and Interior Laboratory Dual Spacecraft mission. Analyzing these variations in the Moon's gravity field allowed us to peek under the Moon's surface and see what lies beneath. This confirmed that Grail data conforms with ilmenite layer simulations. Such confirmation also showed that gravity field observations could be used to trace the distribution of ilmenite remnants left behind after a majority of the dense layer had sunk to the deep interior of the Moon. Our analyses show that the models and data tell one remarkably consistent story. Ilmenite materials migrated to the near side and sunk into the interior in sheet-like cascades, leaving behind a vestige that causes anomalies in the Moon's gravity field, as seen by Grail. An artist's illustration shows two solar-winged spacecraft connected by wiggly lines representing communication. The lines extend to Earth, the spacecraft float above the Moon. Artists' concept of NASA's Grail mission. Grail's twin spacecraft are flying in tandem orbits around the Moon to measure its gravity field in unprecedented detail. The team was also able to determine when the Moon flipped inside out. They say the interruption of gravity anomalies by large and ancient lunar impact basins indicates the ilmenite-rich layer sank prior to these impacts. This cross-cutting means the sinking event would have happened earlier than 4.22 billion years ago, indicating that the sinking could have triggered volcanism, which was seen at later times across the lunar surface. This research also adds nuance to an interesting picture of the Moon we see today. The overturn of the lunar mantle billions of years ago would have led to the creation of a dark region known as the Oceanus Procellarum region, as well as on the side of the Moon close to Earth. This area of the Moon is lower in elevation and has a thinner crust that's mostly blanketed by lava flows, unlike the thicker crust of far side regions of the Moon. It also has a higher concentration of rare elements like titanium and thorium. It turns out that the Moon's earliest history is written below the surface. And it just took the right combination of models and data to unveil that story. Thank you very much for watching. Goodbye.